Hello, students. Today, we'd like to talk about some techniques in solving linear systems of equations. This is something you've actually done many, many times in your previous courses, especially in general math, Algebra 1, and Algebra 2. But what we want to do today is to introduce a technique dealing with matrices, which you may have actually already seen in a Algebra 2 class. The introduction of matrices to solving linear systems is very effective, it's very efficient, and it's something that you can use with digital computers. So the theory that we are actually discussing is a component of what we call the discipline linear algebra. And many of you as STEM students will actually eventually take a course in linear algebra after you finish the calculus sequence, or you may actually take the linear algebra when you have completed calculus 2. Again, you may also take a course in topology and differential equations, but these will introduce very, very useful techniques that will be important to a STEM professional. So let me go ahead and share my screen so that we can see some of the techniques that you will be able to use. Now, what I've done initially here is just talk about some of the ideas that we see when we actually introduce matrices. Now, there are three operations with which you are already familiar. That is, when it comes to solving linear equations, we utilize three techniques without even thinking about it. And so if we consider a row of a matrix to actually represent an equation, then we can apply those techniques to the matrix. For instance, we call these the elementary row operations. That is the first operation. For instance, if you write down two linear equations, you can write them down in any order you like. You can interchange them. The same is true for the rows of a matrix, especially when they actually depict the actual equation. You can multiply any row by a non-zero constant. For instance, when you have an equation and you multiply every term by a non-zero constant, you do not change the arithmetic solution. You rewrite the equation. If you multiply every term by the same number, you have not altered any of the arithmetic of the solution. You simply represented the equation differently, an equivalent representation, as they say. And then often what you want to do when you're solving simultaneous equations is you would like to eliminate a variable so that you can actually solve for another variable. And so what you may do is you may multiply a particular equation by a constant, some multiple that will allow you to add said equation to another equation to absorb that particular variable. That technique you do without thinking about it. And for instance, if the two terms that are already that you want to absorb or eliminate are already additive inverses, you simply add the equations. And so you just add the multiple as it is. That is one times the equation, so to speak. That's basically this third operation, elementary row operation, adding a constant multiple of one row to another row. And what we do is we store the result in the row that's listed last, which is the second row here. So the idea is that we do not change any of the arithmetic that we've done before. There is no difference in the theory. We simply apply those operations to the rows of a matrix, which actually represent the equations. Now, when you think about a system of equations, let's look at a very simple example here. And then I want to actually talk about an example where we might have infinitely many solutions. You can look at a system of two linear equations and two unknowns. And the first thing you could think is that, well, the equations could be multiples of each other, so you will have infinitely many solutions. The equations could have no solution because geometrically they may be parallel. They may never intersect. Or the last possibility is that the equations do intersect. That is, you have a unique solution. So all of the theory that you learned previous to this class is still at play here. We're simply representing the equations that we are working with in a system as rows of a matrix. And then we apply the elementary row operations. Now, what we want to try to do is to simplify the actual coefficients of the matrix so that we can easily determine the solution. And I'll show you how we do that. It's actually quite interesting and somewhat fun to do. It will take a little bit of just getting used to, but if you keep going back to what you did before and applying the same technique to the rows of the matrix, then you will see that they are indeed equivalent. So let's look at a very simple equation or system of equations from your lecture notes. That is, we have 2x minus 8y equals -4, and we have 2x plus 2y equals 3. Now, what we want to do to transfer this system to a matrix is to simply write the coefficients of x and y and the right-hand side in that order. That is, we have 2, -8, -4. Now, what you might think of is this as being the first column as being the x, the second as being the y, and then a right-hand side. Now, you're thinking X, Y, Z, W, X, Y, Z, those are great numbers for variables, just our regular alphabet. You can also think of utilizing subscripts. Notice here, I have a matrix that has 3 rows and 3 columns, and I've designated the row first and the column second. So we look here, we say row 3, column 3. We look here, we say row 2, column 2. We look here, we say row 1, column 2. So subscripts will actually give you an infinite number of variables if you would prefer to use that. It is simply your choice. The selection of a particular variable is always the choice of the person doing the calculation. Now, for instance, if you're doing a particular problem in homework where certain variables are specified and then you have to actually enter a solution, then the actual letters that are used in the problem must be used when you type the solution for obvious reasons. But when you're working a problem and you're setting it up yourself, you can use any notation you like. Just be consistent with the mathematics. Now, for the second equation, we have 2x, 2y equals 3. So we write 2, 2, 3. Now, there is a notation that the book uses and some other books use, is that they will put a vertical line here for the equals. I'm not always going to do that. You certainly can do it, but it's not required. I don't want you to think that you need it. In usual cases, when we're working with the matrix, the actual column that is rightmost will designate the right-hand side. So if you would like to put the vertical line there, that would be fine. That will not change anything. But for now, I will actually leave that out. Now, notice when we look at this, one thing that we want to do with the row operations is to achieve what we call a row reduced echelon form. Now, this technique, I'll just write it, is called Gauss-Jordan reduction. Gauss-Jordan reduction. And the goal is row reduced echelon form. Now, in some cases, it's easier just to give you an example than to try to explain this the first time you go through it. What it basically means is that we want as many ones and zeros in the matrix that we can actually create, so to speak. We may be stuck with some other numbers that aren't ones and zeros, but we can't do anything to improve upon that. But the more ones we have, which we will call the leading ones, and the more zeros we have, the easier it will be for us to state the actual solution. So let me give you an example of what I mean by that. Now, when we look at the initial matrix, the first thing we want to think of is being able to have a 1 here so we can say x equals some number, if possible. So in order to create a 1 here, the first thing we're going to do is we're going to multiply the first row by 1/2. Now, the notation that you'll see often in textbooks is that you'll use an uppercase letter to denote what the result is. That's extra notation that I think is not essential. It really doesn't give you any extra information. It just clutters up your work. So in order to write this particular operation, which is number 2 here, we're going to say 1/2 row 1, and we'll just put that in the new row 1. That becomes the new row 1, so to speak. We're not going to just call it uppercase R sub 1. That's not necessary. So if I would like this to be a 1, I want to multiply each term in the first row by 1/2. So we have 1/2 R1. So that will give us a 1, a -4, and a -2. We just divide by 2 or multiply by 1/2. That's the new row 1 right there. Now, what we're thinking is, in order to create more zeros, that is, where do we need the next 0? Well, once we create a leading 1, we want a 0 below that leading 1. If we can do it. Well, maybe there is no row. Maybe there's only 1 row. But if there's another row, what we want to try to do is make a 0 right here. So the idea behind the Gauss-Jordan reduction process is to create as many 1s as zeros. So now we would like to make a 0 here, but here's how simply we do it. You're thinking if we have a 1 in the row entry above, then that makes the process easy. So now we simply multiply this row by the additive inverse of 2, which is -2 row 1, and add to row 2 and put that result in row 2. So now we say, in this case, -2 here gives us a -2 plus a 2, which is 0. -2 here gives us a +8 plus 2, which is 10. -2 here, again, gives us a -2 times a -2, which is a 4. Add to 3, we get a 7. So it's the same process that you do when you have all the x's and the y's together and you add things. You get the same result, but you don't clutter up the process with the variables, which are now aligned in the columns. Now notice the improvement here. We have a 1 and a 0. Now, the next thing that we want to do is to move over to the next column in the second row and create a leading 1, which will be the leading 1 for the y variable. So here we want the leading 1. So just to see how we did this one here, we're thinking we're going to have to multiply row 2 by 1/10. That will create the 1 here. So we have 1/10 row 2. So 10 over 10 will give us 1, and 7 times 1/10 is 7/10. Again, very good. So now we're like, oh, wait a minute. Let's read this equation here. Y equals 7/10. That's what y is. We're done with that. That is, as we create the zeros and the 1s, we make it really easy to read the solution. But we can't do that for this. We're thinking we've got a 1 here. We could create a 0 here and then be able to say what x is. So the idea is that when we get these leading 1s and we have the zeros below and above, then that makes the process of reading the solution very simple. So now when we look at this, we're thinking, well, how can we make the 0 here? Well, we can multiply this row by 4 and add it to the first row. So notice row 2 is multiplied by 4. We add to the first row. So the 0, of course, doesn't change anything. So we have 4 plus a negative 4, which is 0. And now here we have 4 times 7 right here. And then we have a denominator of 10. So we can go ahead and write -2 with a denominator of 10 to have -20 over 10. There's many ways to do this, but since we already have the 10 here, don't bother to reduce it yet. Just go ahead and write it this way. So now, of course, we have 28 minus 20, which is 8. So we have 8 over 10. And now we can say, well, it's okay to reduce it. So divide by 2 in both cases. The 2's absorbed and we get 4 over 5. So now we have a 1, 0, 4 over 5. Now notice, this is what we call the reduced or row reduced echelon form, because now we have as many zeros and ones in the coefficient matrix as we can stand. So if you just covered this up, you would basically just say that's a 2 by 2 identity matrix. And we'll say more about that in the next section. But that's a 2 by 2 identity matrix. It serves the same purpose as the multiplicative identity 1 when we, in the real numbers, the 2 by 2 identity matrix is actually an identity, when we multiply it by another 2 by 2 matrix, it does not change it. So that will be a property that we talk about extensively in the next section when we just discuss the arithmetic of matrices. So now what we can see is X equals 4/5. That is when you write this down, we have X plus 0y equals 4/5. So X is 4/5 and 0x plus 1y equals 7/10. So y equals 7/10. Now, if you actually went back to the method that you learned in general math and algebra 1, it would be exactly like this. And you might be thinking, well, you know, in the 2 equations, 2 unknowns, I'm okay with the old method, and I wouldn't disagree with you. But in order to master this technique, you need to start with systems that are very knowable to you, that make sense to you. And then the more abstract systems will make more sense. So again, as you look through this process, you want to create the leading ones with each column. So you'll have a leading one, if possible, for each variable. And then you can actually read the solution. Now, of course, what's nice about the matrices is that they actually tell you when you have no solution, just because you get inconsistencies like 0 equals 1. That's inconsistent in any book. Okay, so if you get a row that reads that, then you know you have no solution. And of course, you'll check your arithmetic to make sure you got it legally. But the important thing to notice here is by creating the leading ones and the zeros, we make it very simple to read the solution. Again, remember, the elementary row operations are exactly the operations you always use to solve systems of equations, and especially the linear ones, which you did in your previous courses. So we're not changing any of that. We're just adding the matrix in order to make the process more efficient. Now, what I wanted to do, ladies and gentlemen, is talk about 2 simple situations where we would have just, for instance, one equation. Now, what I've done here is I've just written down equations in isolation. So here's just like one system. Say you just had 2x plus y equals -3. Well, if you had to solve that system, you would know there would be infinitely many. But what I did now, and this is separate, these are not connected, I just wrote down another system here, 3x minus 2y plus 2z equals 5, and that's the entire system. And what I want to show you here is that even when we're just working with one equation and 3 unknowns, we can still process the solution. You're thinking, well, where are the other 2 equations? Well, we don't always have that. And I want you to understand that in terms of matrices, we can actually process the solution just as we would need to in other maybe larger situations where we have more equations. So notice, if we just restrict to this one equation and three unknowns, so write that down. One equation, three unknowns. Now, when you look at this, you're thinking, okay, we have the 3, the -2, the 2, and the 5. X, Y, Z, right-hand side. And we're thinking, well, what do we do with this? Well, we could get a leading 1. So we want X equal, so we can divide by 3 or multiply the row 1, which is kind of redundant. I mean, there's only one row anyway, but 1/3 row 1 will give us 1, -2/3, 2/3, and 5/3, and that's it. We've got one leading 1, and there's nothing else we can do to this. We can undo what we just did, but that's ridiculous. So now here's our equals 5/3. So this says X minus 2/3 Y plus 2/3 Z equals 5/3. Well, what we tend to want to do is to put everything on one side so we can solve for X. So X is 2/3 Y minus 2/3 Z plus 5/3. Now, at this point, you could think, well, we could assign Y and Z to be parameters or just leave them as Y and Z. What we see here is that the Y and the Z are variable. They're free. They're free in that they can be assigned any value. So we would say here, Y and Z are free. What that means, ladies and gentlemen, is that they do not have specified values. And X will depend on Y and Z. So this will give you infinitely many solutions. I mean, if you have one equation and three unknowns, there are infinitely many solutions. So to make it understandable, we simply can think of Y as being a parameter S and Z as being a parameter T. Now, the only reason I'm writing this is that you may see it written this way. In some instances, we just keep the same variables and don't change them to other letters. In a lot of linear algebra text, they will use parameter letters like S and T just for convenience. It's not required. Doesn't matter what you call it. If it's free, it's free. So what we would say here is that S and T are just real numbers. They're free because Y and Z are free. So now you can see that X can be determined if you determine a value for Y and Z or a value for S and T. So for instance, if S was 0 and T was 0, Y equals 5/3. But if you start changing the numbers around, you get a very interesting situation. Now, what's interesting about this, notice here, if S equals 1 and T equals 1, these just absorb, and you still get 5/3. So then you're thinking, okay, well, let's think of it this way. Say S is equal to 1 and T equal to 0. So then you get 5/3 plus 2/3, and that gives you 7/3. So for different values of S and T, you're going to get another value for X. And when you get that, that means you can generate as many values as you like. So we would say infinitely many solutions, as opposed to what we had on the last problem, which was what? A unique solution. And let me write that down. Unique solution. So when we think about the matrices, ladies and gentlemen, we see that this provides us an avenue to consider situations where we may have infinitely many solutions. Now, of course, we may restrict the values of the free variables. Maybe we're working a problem where the free variables would only need to be maybe non-negative. Negative values wouldn't make any sense if we're doing, say, a production problem. So again, what's important about the matrix technique is that it provides an avenue to redirect the variables in a way that provides more information. So now when we run from here to here, just by getting the leading one, we can easily solve for X and then see that we will get infinitely many values for X. And then of course, there's nothing sacred about X. You could solve for Y in terms of X and Z. You could solve for Z in terms of X and Y. That is simply your choice. The nice thing about this particular problem is that we like to order our equations and then we actually attempt to solve for them as neatly as we can. So I wanted to give you an idea of what it meant to have infinitely many solutions in a context that is easy to figure out. Now, here's another situation. Here's an example from your homework where you have what we call the reduced or the row reduced echelon form. Reduced row or row reduced, I think it will be said many similar ways like that. So we'll say row reduced echelon form. And so sometimes this is called RREF. In some of your fancy calculators, students are always happy to see the RREF because it does the calculation for them, which again doesn't give you any practice in actually working the technique. The important thing about the row reduction process is that it apprises you of the arithmetic that you need to use in order to arrive at a solution, and that's very important. So again, this is basically an acronym for row reduced echelon form that's just quicker to write. Now, here's a problem from your lecture notes where you basically have the row reduced echelon form. Notice we have variables W, X, Y, Z, and notice we have as many ones and zeros as we can stand. We have a leading one, zeros, leading one, zeros above and below, and then the leading one here and zeros above. So I'm going to give you another term now. This means we can solve for X, Y, W, X, and Y. So we say W, X, Y are basic in the sense that they depend on some other variable or are actually unique. And then the actual variable that has no leading one, Z, just like before, is free. Remember in the previous example, we might as well go back. The Y and Z are free, but X is basic. I was focusing so much on the free, I'll go back now and include the basic. So now we see that if we have a leading one associated with the particular variable in the column with which it is associated, we term that variable basic. And then, of course, poor Z doesn't have a leading one. It has ones in it, but they're not leading ones. And so in this particular case, what we see is that Z is the parameter. Now, notice what I've done here. I said that you could actually write this as a T parameter, but I left these all in terms of Z because this is often the way the text will write it and not change the letter, which of course is not required at all. Just giving you some ideas that you may consider if you see things written differently in another source that you may be using. But notice the reduction process has already been done. The Gauss-Jordan elimination or the Gauss-Jordan reduction has already been performed on this matrix. So now we can simply go right to the equations. That is now transposing everything. W is now -1 minus, we think of subtracting, minus Z. X is now 9 minus z, and now y is negative 5 minus 7z. So I've just skipped the step of writing down all of the variables on one side. I just left the basic variable on the left and moved everything else over with the free and the constants. So now z is free, as we see here, and you could actually write this as a solution set with a 4 tuple. That is, now w is 1 minus z, x is 9 minus z, y is negative 5 minus 7z, and then, of course, the last coordinate is just z, but z is free. Okay, so now, of course, if you take z equal to 0, then w is negative 1, x is 9, and y is negative 5, just like we did in the previous example. So for the varying values of z, you'll get differing values for what w, x, and y. So again, infinitely many solutions. So you can see that if you were using the old technique of dealing with 3 equations and 4 unknowns, that might get a little bit complicated trying to keep up with the process. So what we're finding is that when we actually write the coefficients in the right-hand sides, and let me just write this up here, right-hand side, when we write this in the matrix form, we're able to efficiently reduce, creating the ones and zeros to provide a solution technique that's easy to read. It's organized. That is, we take the technique of solving linear equations and make it more orderly. And of course, this can be coded. This reduction process can be coded. And that's exactly what algorithms do that do the reduction process. You can think of production processes that have thousands of equations and thousands of variables. It does happen. I mean, maybe that's a little bit extreme, but maybe hundreds of variables and hundreds of equations that require an optimization method. And if you study more finite mathematics, you will talk about some of these methods. So the matrix has really become a revolutionary object. Matrix theory that was developed was a big topic when it first came into the light. So we're finding that mathematics often finds itself heightened when we think of new technological advances like the computer. Number theory is so much more in the realm of mathematics because of its use with cryptography with the computer. And of course, the matrices blend so well with algorithms with the computer because we can simply notate through subscripts and functions where any of the elements of the matrix reside. So we can absolutely use the technology to advance computational prowess when we're having to deal with large numbers of variables and large numbers of equations. Now, there are 2 examples here from your lecture notes that I've written out that I think are very interesting. And I wanted to show you, for instance, if you were doing your homework, how you would write these. Now, of course, if you want to use the vertical line, you can, but I thought these were very interesting equations because as you looked in the last example, we had infinitely many solutions. These are examples of unique solutions. Now, remember when you were in Algebra 1, your teachers would always say, if you're dealing with the Cartesian coordinate plane and Euclidean distance, 2 points determine a line. But now, of course, if you're dealing with a quadratic function, that is ax squared plus bx plus c, you need 3 actual points on the curve to determine the unique function. Okay, so we can actually think of the matrix theory as a way to actually solve for the coefficients. Now, here's what the problem gives us. We're given the point 1, 0, the point -3, -8, and the point 316 as being elements on the quadratic function, or just elements of the function. We know ordered pairs determine functions. And so I've written over here, f of x equal ax squared plus bx plus c. And from the knowledge of this, we should be able to determine an a, b, and c that will define the unique function. So now what we do is we use this equation to set up three linear equations. So we substitute, for instance, let's do the easiest one first. Let's just substitute 1 for x. So we just get a plus b plus c equals the y coordinate, which is 0. That's the easy one. Now let's just look at the substituting -3 for x. Well, when we square -3, we get 9. So we get 9a minus 3b plus c equals -8. Of course, the c is not going to change, or the coefficient of c will not change because there's no x. And then for the 3, what's the difference? Well, we've got a different value for the right-hand side, but of course here 3 times b gives us the 3b as opposed to the -3b when we have the negative value for x. So we've got 3 equations in 3 unknowns. So this simply utilizes the functional equation for the quadratic and then the values that we have for the x and y coordinates. So now we have what we call a linear system, 3 equations, 3 unknowns. Let me write that down. 3 equations, 3 unknowns. Very simple. So now what we can do is we can take the equations and write them in the matrix. Now, of course, I thought about this, and we want to do leading ones, right? We want to get those leading ones. So since we have ones here for the coefficients, we'll just start that first. That is, we have 1, 1, 1, 0. And then we'll go up to this equation here. We get 9, -3, 1, -8, just looking at the coefficients. So now you can think of A, B, C, right-hand side. And then, of course, for the last equation, we have 9, 3, 1, 16, 9, 3, 1, 16. So at this point, the process, even though it's a little bit longer, is certainly very simple. Notice, in order to get the zeros here, we're going to take -9 times the first row and add it to the second row. And we're going to do the same for the third row. That is, we're going to multiply -9 times the first row and add it to the third row too. So again, -9 plus 9 is 0. -9 plus -3 is -12. -9 plus 1 is -8. And of course, the 0 doesn't change anything. Now let's do the -9 again. -9 plus 9 is 0. -9 plus 3 is -6. -9 plus 1 is -8. And of course, the 0 doesn't change anything. So we're doing really well in the first column. We've got our leading one and our 2 zeros. Now, just like we had before, we move to the next column looking for a leading one. -12 is certainly not 1, so we can multiply row 2 by -1/12 to make that into a 1. So we have 1 here, and then, of course, we have -8 over -12 gives us a 2/3. And then, of course, here, the same thing, 2/3. You can go ahead and reduce. In some cases, we may not reduce because it may ease the arithmetic a little, like we had in the first example, but you can always go back to that if that's necessary. Again, you can apply whatever techniques you need to make the arithmetic simpler. So now when we look at this, we've got the leading one, but we don't have the 0 here. So now, of course, we can multiply this row by 6, which is the additive inverse of -6, to make the 0 here. So we say 6 times row 2 plus row 3. So 6 plus -6 is 0. 6 here. 3 into the 6 will be 2. 2 times 2 is 4. 4 plus -8 is -4. Same here. When we multiply by 6, we have 3 into 6 is 2. 2 times 2 is 4. 4 plus 16 is 20. So we're seeing that the arithmetic is the same as we would have with the old method, but it's so much more organized. And it's easy to go back and check because you've got everything written out as to exactly what you've done. Now, notice here, we've done a great job, at least working with the zeros here, and we need a leading one here, which we can just get by multiplying row 3 by -1/4. So when we do that, of course, we get the 1 here, and then, of course, 20 divided by -4 will be a -5. And look, we already know now what C is. C equals -5. As you can see, it's written right there in the last row. So we're thinking we need to work back up and get B and A. So what do we need? Well, let's just look here. We need a 0 here, a 0 here, and then eventually a 0 here. So by looking at the technique that I'm teaching, it shows you an order that will work. What you don't want to do is create a 0 and then undo it. So make sure that you're working down the columns, then you move over to the next variable, make the leading one, work downward, and then work back upwards from the right side of moving back to the left. So now we look really good here. So let's see, what can we do to make these zeros? Well, of course, we need a -2/3 times row 3 to make that a 0, and then, of course, just a -1 to make that a 0. So again, we have, notice here, this is the nice part about when you're working on the bottom row, these zeros don't change anything here, because certainly we wouldn't want to undo the 0 and 1. So that's fixed. So -2/3 plus 2/3 is 0. And here when we do a -2/3, we get what? -2/3, we get a 10/3 plus a 2/3, which is a 12/3, which gives you a 4. Let me write that out. Notice you have negative, in this case, 5 times a -2/3. The negatives absorb and give you 10/3. And then when you add the 10/3 to the 2/3, that gives you 12/3. 12/3 is 4. And so we have the 4 here. Okay, so that's the computation that we're doing. And not very difficult. And then then that's pretty much it. Now again, what's interesting about this technique is that you write down exactly what you're doing, and you can just go to the row and operate on it, and then write it here. Now notice, to make this 0, we need the negative here. The negative, or the additive inverse of 1, is -1. So again, zeros, no change. The 1 and the 1, they're preserved. And so -1 plus 1, 0. And then the negative of -5 is 5, plus 0 is 5. So there's nothing there. There's a little scratch there. So we've got 5. Notice we don't know exactly what's going on here. We see now that y equals 4. So B equals 4. So we're check here and check here. Now what we see is A plus B equals 5, but we just want A. So now again, very simple. If we multiply row 2 by -1 and add it to row 1, we get the 0 here. So again, 0, no change. -1 plus 1 gives us the 0. Here, the 0, no change. And then, of course, -4 plus 5 is 1. And so now A equals 1. Check. So let me just say one thing here that's important. Once we get to the leading one here, ladies and gentlemen, we want to work back up with this row. Make a 0 here and a 0 here. Once we have that, the last 0 that we need to create is above the leading one here, which we've got here. So as we work down to this leading one and then work back up, so we go basically left to right and then right to left, we don't undo any of the zeros that we've created. That gives us a method that's not only efficient, but correct. So now notice, and I don't put the vertical line here, which you can put if you want, but now we see we have the row reduced echelon form here, row reduced echelon form, RREF. And what we see at this point is that we can easily read. So let me just remind you, A, B, C, right-hand side. So again, A is 1, B is 4, C is -5. And so when you write your quadratic equation, we have AX squared plus BX plus C. So we have X squared plus 4X minus 5. And this is our unique quadratic function. So when it comes to the Gauss-Jordan process to achieve the row reduced echelon form, then we're fine. That is, if you think about the process, it does exactly what you've done before, but it is much more organized, and you don't spend pages and pages writing down A, B, and C unnecessarily. This puts all the information where you need it, and you can operate on the rows to produce the row reduced echelon form, which will allow you to read the values. Now, of course, as you do this, you have to, again, think about what you're doing and where the arithmetic is taking you. But remember, when I write this, we multiply row 3 by negative 2/3, add it to row 2, and that's where the result goes. That is, the result goes in the row that's listed second. When we multiply row 3 by -1 and add it to row 1, that's where we want the result, because notice we want the 0 here. -1 plus 1 is 0. And that's where we want to record the result, because we want to put the result in the place that produces the maximum number of zeros and ones. Okay, the leading ones are done first. They help us create the zeros. You move to the next column, leading 1, create a 0. Move to the next column, leading 1, create zeros. Again, you can write down definitions for row reduced echelon form all day long, but that's not going to help you do the actual process. Practice the process as I have described here, and you will have excellent results. And you will actually start to like this because it is so incredibly efficient. Now, what I have here is another problem from your lecture notes, which is, again, the same size as the problem we did here, but an interesting system. That is, notice here, this is from your lecture notes. You have x minus y equals 5. So we have 1, -1, 0, 5. And again, think of x, y, z, right-hand side. We had a few fractions here. It looks like we have a few fractions here, but they're not difficult. Fractions can be difficult, but again, think about number theoretic concerns, just like I did here, to help you in producing the correct arithmetic outcome. Here we have 7x minus 3z equals 49. So we have a 7, a 0, a -3, and a 49. And then for the last equation, we have 7y plus 2z equals 14. So 0, 7, 2, 14. Just like the last problem, we want to create as many ones and zeros as we can. Notice here we have a leading 1, so we're ready to go. Look at that, such a gift. We have a 0 there. So when you write down your original system and you've got ones and zeros in advantageous places, part of your work has already been done. Notice with this problem, we didn't get a whole lot. Well, we were grateful for the 1 here, right? But the interesting thing is that 1's not going to be preserved. We have no way of preserving those 1's. That is, but at least here we had the gift of the leading 1. Now here we have a leading 1 and we have a 0. Those are two entries that we can preserve, that we do not have to create. So now let's just look here. Let's analyze. We need a -7 times row 1 and add it to row 2. So write the operation right here. So we have -7 plus 7 is 0. -7 times -1 is 7 plus 0 gives us 7. The 0, no change. And then -7 here gives us a -35 plus 49, where those are just multiples of 7. That gives us a 14. Now, there we have it, 1, 0, 0. Excellent. Next column, need a leading 1, so we've got to divide by 7. So 1/7 times row 2. So again, 7 over 7 is 1. -3 over 7. Again, write as a fraction. No decimals. Don't do it. Just write as fractions. And then, of course, 14 over 7 is 2. Got the leading 1 ready to go to make that a 0. Okay, how do we make this a 0? We multiply row 2 by -7. Notice I've written this here. -7 times row 2 plus row 3. Let's do it. Notice the 0, no change. -7 plus 7, 0. Now here we have the -7, but the 7's absorbed, and the negative gives us a 3. 3 plus a 2, 5. See, when you write in the fractions, of course, if the numerators and denominators absorb, that just leaves you with an integer. So the symbolic calculation is so effective. We do that all the time, absorb. That's what we're doing. And then let's look at the very last bit. We're going to multiply. Well, the gift keeps on coming. Here we have -7 times 2. That's a -14. -14 plus 14, 0. So boom, boom. We already know what the z is, but let's just go ahead and get the leading one because that's what we're supposed to do. So again, we have to multiply row 3 by 1/5. So no change, no change. 1/5 times 5 is 1 and the 0. So boom, just like we thought right here, z is 0. We already have that right there. That's done. Bottom row, z equals 0. That's it. Now we want to create the zeros here, but notice that is still preserved. That 0 up there, that's a gift. We don't have to create that. But to make the 0 here, we have to multiply this row by 3/7. So 3/7 plus a -3/7 is 0. And then, well, 3/7 times 0 is 0 plus 2 is 2. Well, this is really simple compared to the last one. I mean, if you got zeros, then very nice. Okay, the very last one, we know we've got all these ones and zeros. We need a 0 there. So notice we can just add these two rows, row 2 plus row 1. So no change. 1 plus -1, 0, no change. And then, of course, here, 2 plus 5, 7. That's it. The only time we had to do any work was add 2 and 5, and that wasn't very challenging. So notice now we can read it. X equals 7, Y equals 2, Z equals 0. Unique solution. So just remember, the Gauss-Jordan technique will be something that you will continue to use, especially when you get to Calculus 3. And when you get to linear algebra, you will already know the Gauss-Jordan technique in the row-reduced echelon form, which is going to take you a long ways into linear algebra. When you perform these calculations, you're actually doing work with vector spaces. And you will continue to do the same technique over and over. It's kind of like we can't really get rid of algebra, can we? When we take calculus, we do algebra all the time. When you do linear algebra, you'll be doing the Gauss-Jordan technique, the row reduction process, to produce as many ones and zeros so you can move the calculation forward. And then the arithmetic opens up to more abstract spaces. So as you learn this technique, you will find uses for this in other STEM classes, especially science and engineering. And as you take more mathematics, you will definitely have uses of this. So let's look at the linear system, the Gauss-Jordan process, as a departure from the types of mathematics we have been doing, especially with the logarithms and the exponential functions and the theory of equations, but a very nice departure that gives us a window into other disciplines in mathematics that can be very, very useful to us. So remember, as you work on these types of problems, think about models, just like we had models with growth and decay and Newton's law of cooling. Now we have models with linear systems. And we can use the efficient technique of the Gauss-Jordan process to be able to effect a very clean solution. So enjoy the row reduction process and use the techniques that I've shown you here. I think you'll find them to be very effective and very, very teachable. For instance, you can describe very arithmetically the types of processes that we've been doing, but the first time through, that is not as effective. You need to get used to creating the leading ones and the zeros, and then working through the matrix, developing your confidence, and then becoming accustomed to the row operations. Okay? Well, I hope you enjoy this process. I think it'll be a lot of fun. And I'll talk to you soon. Thank you.